Okay, good afternoon, everyone. I'm Rajesh Gopakumar. I know you've all come to hear Eduardo and not me, but I'm sorry, but I'll have to inflict a little bit of an introduction to ICTS, especially since at the beginning of the meeting we couldn't do that. So since most of you are perhaps here for the first time, I'll give you a very quick glimpse. I promise you it won't be too long. So it's a pleasure, of course, to have this meeting here. And I'm particularly glad that Eduardo accepted our invitation to give this ICTS distinguished lecture as part of this meeting. But what is ICTS? So let me just give you a little bit of a bird's eye view, both photographically as well as maybe in words. So this was actually the picture of ICTS pre-pandemic in some ways, and I've been using this picture for a while, but I realized that the pandemic has made many changes, so you can sort of contrast. So now the tree cover is hiding many of the buildings here, and so that's just in 4 or 5 years. In any case, what is ICTS as an institution? It's something which intertwines three components to our, there are three components to our mandate. Firstly, we are a part of the Tata Institute of Fundamental Research, TIFR, which many people often identify with the Bombay campus in Mumbai, but TIFR is now sort of has many centers, many spread across the country in some ways. There are 3 centers in Bangalore, one in Hyderabad, then Pune, and so on. And each has its own mandate. And ours is to function in some ways like the KITP, which is probably something familiar to most of you in the audience. But unlike many of these sort of peer institutions, we come, I think, with our unique profile, which means we have research together with these programs like this one and a significant outreach component. And unlike, say, KITP, our programs actually span a variety of disciplines in theoretical physics, of course, but also mathematics. About half our programs are in mathematics and computer science, and together with quantitative biology, climate sciences, and other things. So we interpret theoretical sciences in a very Catholic sense, and I'll tell you a little bit about the programs that we have. So this is a watercolor of that library building, which maybe you have by now had a chance to explore. Just go down that walkway and you'll see this sort of unusual building. Do go inside, and it's a nice place to just sit and sort of be inspired. And I think it did inspire a visiting mathematician who painted this watercolor. And I keep telling people, if you have similar inclinations and are sort of, and you have something, we'll be very happy to share, highlight it. So this collage of our research faculty, Sumati, of course, here, but we have about 30 plus faculty in varying levels of, some are long-term, some are joint faculty, etc. We have an active PhD program which has a large, over 100 students now, and postdocs about 30. We don't have departments. We have people who have strong core strengths, but we try to look for people who can converse across disciplines. And in the physical sciences, in the mathematical sciences, we have people in these areas. In climate sciences now actually is a kind of a thrust area, but kind of naturally growing out of things in PDEs and dynamical systems, algebra, geometry, and mathematical physics, in probability theory, theoretical computer science most recently. That's an area, again, we are growing in. In the physical sciences, there's astrophysics, and something that needs to be now, you can see it's like become a gigantic list, but this is really to be sort of thought of as people in condensed matter physics, statistical physics, also fluid dynamics, and quantitative biology, and finally string theory and quantum field theory. So the programs of ICTS, so these are some new, this is sort of, you can see the poster for this program, but many others we've had in the recent years. We have a program calendar, which is like chock full. It's all 52 weeks essentially of the year. But the way these programs are organized, they are open to the global scientific community, not just in terms of participation, but in terms of organization. So there's a call for proposals like KITP has. It's twice a year. December 31st and June 30th are the deadlines, so middle of the year, end of the year, very easy to remember. And that's the deadline. And so the next deadline, December 31st, is for programs from starting from March 2025, April 2025 till September 2025. So if you want to organize a program 2 weeks or longer, your chance to submit, you have a chance to submit till December 31st for that window. Till March 2025, we are completely booked. Though we do try to fit in things called discussion meetings, which are sort of smaller ones, less than 2 weeks, depending on availability of slots. But a typical program like this one is 2 to 3 weeks long. There's a pedagogical component, which we take very seriously because that's one of the aims of ICTS. I think perhaps we emphasize that more than, say, KITP, because one of the aims is to have the Indian community, especially of students, postdocs, get exposure to various frontier areas of research and to be able to interact with some of the best scientists from within the country and abroad. And so this number actually needs to be revised. It's about 35 plus now per year, and nearly 3,000 participants, with about a third of them being from outside the country. So I think in a fairly short while, we've become a science hub for the country's researchers, and I think a lot of new collaborations and ideas have been coming out. I stress this, that we've had over 600 publications. We've been collecting data in the last 5 years, and over 600 publications that have acknowledged ICTS programs for the fruition of the work. So if there are works that come out which you feel your presence here helped, please do acknowledge, please do let the program office know. They have a kind of a template for wording it, and then they can keep track. And of course, funding agencies take it very seriously. This is very useful to convince them that ICTS is worth continuing. All our talks are archived, and especially for the younger people, I urge you to view this YouTube channel, ICTS Talks. You just have, it's there on our homepage, the YouTube button. And it has now 7,000 plus lectures of very high quality, ranging from, of course, the technical lectures in schools and workshops like this to introductory lectures aimed to the general public, etc. So it's I think, a very wealthy repository. We have special lectures, and the distinguished lectures are one of our special flagship lectures, and we are very happy that we have one right now in this program. But if you want to look at some of the other series of lectures, like the Chandrasekhar lectures and so on, again, the YouTube channel is the best place to look at it. Let me just conclude by some words about our outreach, which is the third component of our mandate. And we do science communication. I think Yuval will be giving a copy with curiosity talk at the planetarium, perhaps this weekend, the coming weekend. This is something that we hold at the planetarium, and we have once a month. Vigyan Adda is another program that we have for undergraduates, so not quite at the lay person's level, and that's a purely online thing we started during the pandemic and has been continuing. So we do science communication, but we also sort of diversified recently into more interactive science through exhibitions like this online exhibition called Cosmic Zoom, which is essentially exploring the universe at different length scales. And PRISM, which is Promise in Science and Maths Park, which are for school kids in the Bangalore neighborhood. And we also have been going to some of the local schools here to kind of to help with science pedagogy. Math circles is something ICTS has been spearheading, and we've started an in-person session, and I see Sam here, who has been Sam and others jointly at RRI at the Raman Research Institute. We conduct these sessions to identify and nurture mathematically talented kids. And if you want to actually, any of you want to volunteer for that, students and so on, we welcome that. I mean, you can maybe even talk to Sam if here, or write to the email address, because we are looking to have more institutions partnering in this. This is, I think, a very important thing for the future in the country. So, okay, so that was it. And now we can get on to the real talk. So for that, I'll introduce Ganpati, I think, who will, I'll invite Ganpati to introduce the speaker. And yeah, thanks very much.
Hi, everybody. It's a great pleasure to introduce Eduardo Fradkin, who is a very, very distinguished professor and very well known in the condensed matter community internationally. And Eduardo is from Argentina. He was born in 1950, and I'm not going to be able to tell you his entire life story, but so don't get afraid. But he got his PhD. He actually did a brief stint as an experimentalist before he came for his PhD. And then for some reason, I don't know why, he decided he wanted to be a theorist. But then he did his PhD in Stanford with Lenny Susskind, who many of you have heard of. And he wrote some very important papers on field theories, duality, phase transitions, various things like that, especially gauge theories, confinement, all those things. And in the last, I would say, 25, 30 years, he's done a lot of work on the quantum Hall effect, flux attachment, et cetera, which I came to know after I started working on the quantum Hall effect. Anyhow, so Eduardo has, as befits his status, has gotten lots and lots of awards, honors, everything, etc. He's a named professor. He's a Willett professor at the University of Illinois at Urbana, where he has been since, essentially his entire postdoctoral and, professorial career. And he's also the director of the Condensed Matter Physics Institute at the University of Urbana at Illinois. He won the Guggenheim Fellowship in 1998. He's a member of the American Academy of Arts and Sciences, and he's also a member of the National Academy of Sciences of the United States. Now, after all these positives, I felt that I should say something a little bit negative about him. I was asking him, and he couldn't come up with anything. So I did a little bit of digging, and I came up with a shocking fact, a very shocking fact, which is that his middle name is Hector. So with that,
we have a small ritual, and I'd invite Yuval to come and hand over a memento on behalf of ICTS, the organizers, and school, the program, to Eduardo. It's a sandalwood Buddha.
Okay, thank you for inviting me. It's the first time here, not only at the Institute, but in India. So it's a nice experience, although I have known many people, particularly the organizers, but also some people in the audience from other places. But it's good to be here. It feels great. Okay. So I hope, I am beginning to regret the topic that I get. I'm not sure if it is appropriate for in a colloquium style. I'll do my best, okay? So this is the problem, okay? So this is going to be about duality in condensed matter physics and field theory and other areas. As you know, as Genpati pointed out, I started my career, well, I was an experimentalist very briefly until I broke too many things. But I worked in a high energy group, essentially. So I have ever since, I have been infected with field theory, and I apply it to everything from the growth of tomatoes to everything else, okay? So in fact, many people in our field believe that I am a closet particle physicist for some reason. Okay, I don't know if that's correct or not, but we'll see, okay? So I'm going to talk about the problem of duality and its applications. And duality is a vastly used and misused term. There are many things that are called dualities, and some of them have mysterious connections with each other that people didn't understand them for a very long time. Okay, I'm going to go to the first one. Oops. Yeah. Some text missing here. Okay. Never mind. Okay, so yeah, this is a missing text. Something happened here. So this is back to Dirac. There was some text here about Dirac, which somehow seems to have disappeared now. So Dirac, back in 1931, he looked at Maxwell's equations in some system of units. I like to work in systems of units where h bar is equal to c equals to e equals 2 pi equals to 1. Which is to say, I promise to get the signs most of the time correctly. The factor of 2 pi we can negotiate, okay? So, and factors of c, okay? So as you can see, well, there is a factor of c there, but not in other places, okay? So I am random about factors of c. So Dirac realized that in the absence of sources, namely densities and currents, there is an apparent symmetry of Maxwell's equations under the exchange of the electric and magnetic field. These days, we call this electromagnetic duality. Dirac didn't know that, or didn't actually say it at the time. This actually has a geometric origin. Is the duality, what a mathematician will call a duality of forms, as it turns out. So it has actually mathematical geometric character, but it's an asymmetry once you couple these to matter, because matter couples only to these two equations, whereas these other equations are viewed as constraints. Okay, in fact, these two equations basically say that there are no magnetic monopoles in nature. So he postulated maybe there is a magnetic monopole somewhere, and this is a cartoon of Dirac's monopole. So this was supposed to be a very thin solenoid with some flux that is actually inserted here. And then it looks like a magnetic charge in that case. He also made the statement, which was not understood for many years, that if you actually have a particle with certain electric charge, and you actually transport that around this, what we nowadays call a Dirac string, which is this hello, this thin solenoid. This thin solenoid, in fact, should not be visible. Okay, because in fact, they should carry no energy, because otherwise you're going to get a gigantic energy associated with this object. And then the condition that this is unobservable led to what is called the Dirac quantization condition that relates the magnetic charge with the electric charge up to equals to 2 pi times n in useful units. Okay? And so this actually eventually made it into, for instance, in the detection actually of the Aharonov-Bohm effect, which actually is another manifestation of the same problem. They are using essentially where quantum mechanics enters in a more essential way. But it's the same problem, essentially it's the same concept. Okay, so this is usually, nowadays we call this electromagnetic duality. And notice that it flips, essentially relates electric fields with magnetic fields and electric charges with magnetic charges. And this is going to show up in some things I'm going to talk about later. So there's another thing called duality that was discovered in statistical mechanics. In 1941, there's a famous problem called the Ising model. Actually, it should be called the Ising model, not the Ising model. but let me continue to use that term, is a simplest mode of magnetism where you have essentially spins which are essentially pointing only at some particular direction. So in a sense, they commute with each other. There is an echo? Or is that me? Okay, okay. So the spins can be up or down in some arbitrary direction. Usually you need magnetic anisotropy for that to be true. And I normalize things in such a way that these variables sigma are plus or minus 1. 1 means up, minus 1 means down. And all quantities with units are essentially here in this quantity h that we normally call the exchange constant, divided by the temperature. Again, you see I don't have the Boltzmann constant either. Okay. So if you look at this problem, try to compute this partition function, it's a horrendous problem because if you have a system with n sides A on some square lattice, there are 2 to the n configurations to that. Okay, so that's an impossible problem to solve normally. And so you begin to make approximations. So for instance, suppose that the temperature is very low. And so you're going to have, for the most part, all spins pointing in the same direction. But eventually you're going to have some spins that are going to be overturned. And so the regions where the spins are pointing down versus the regions where the spins are pointing up are separated by things we call domain walls that have a characteristic energy per unit length in this case. Okay? So the weight in a partition function of configuration of domain walls have other questions. You cannot overlap them. They have essentially a repulsive interaction, if you wish, between them. So there is a contribution here to the partition function, which is a weight that goes like e to the minus 2j over t. So why is 2j? It's because it's the energy for flipping a spin. It's a factor of 2 divided by the temperature. It's exponentially small, raised to the length of the domain walls. Okay, then you suppose there is an entropic factor that counts how many of these things are and so on and so forth. So if you go to high temperatures, this coefficient now is very small. And so you can expand this in powers, and then you can do the sums over the spins very easily. And then you can organize this expansion in powers of 1 over the temperature, or the inverse temperature, or actually the hyperbolic tangent of j over t, as it turns out. And it's also an expansion in some sort of loops, okay? But the expansion is a hyperbolic tangent of j over t, that's expansion parameter for the case of the Ising model, raised again to the length of loops. So these are loops on the Dirac lattice, and these are loops on what we call the dual lattice. Okay. So notice there is a concept of duality, and again, that's a purely geometric concept of going from the Dirac lattice to the dual lattice, and it's closely related to this duality of forms mathematically. Okay. So Kramers and Wannier realized that in fact you could, up to some multiplicative factor that can be subsumed in a rescaling of the partition function, that these two series expansions actually can be mapped 1-to-1 into each other up to boundary conditions, okay, which may be important. And then they said, well, we know that magnets have a critical temperature, so let me assume that there is a unique phase transition. And then they said, well, if these two problems are in a sense the same, and that's where the term self-duality comes from, so this is dual to that in a sense, in this sense. So then they conjecture that there is a temperature at which this exponential factor will be equal to that. And then you write down this expression, and you can calculate what DC results. And this was a conjecture. 3 years later, Onsager solved the problem in a way that he didn't quite explain it clearly, but is what nowadays we will say he was using actually some sort of fermions for solving this partition function. Okay, so they are Majorana fermions, if you want to be more picky, and that's what they are. And it turns out that this actually is a correct critical temperature. You get much more from Onsager's solution, of course, than just this. Okay. Of course, the fact that they are dual to each other doesn't prove that there is a unique phase transition. You could have two phase transitions, and one will be mapped into the other. They assume that the transition was unique. In fact, it's the case. Okay, so let me come to this. So now, how about I go now to 3 dimensions? Actually, before I do that, there is another interpretation of this that we will use as we go along. Let me assume that I'm going to call this direction here arbitrary. You know, square lattice is rotation invariant. It's invariant under 90-degree rotations. So arbitrarily, I'm going to call this direction time, actually imaginary time, and this direction I'm going to call space. So you can think of this as a process in which some object or a pair of objects are created, they evolve, and then they annihilate, and the same is true here. So this looks like, they look like particles, whereas these objects are more, you know, we call them kinks nowadays. You will see in a moment why. So there is a quantum mechanical interpretation to this for the people who know StatMech. This is seen more clearly when you use, say, the transfer matrix approach. It's very apparent when you do it. If you go to 3 dimensions now, the situation is rather different. You're still in the low temperature regime, you're still going to get domain walls, but now there are volumes, regions of overturned spins. And therefore the energy is proportional to the area of those regions. And these regions may have complicated topologies, may have handles and all kinds of things. Whereas the high temperature expansion looks exactly the same. So in the case of the height of the analog of the low temperature expansion, is still an exponential like as before, but it doesn't scale with the perimeter, but with the area of the surface of these regions. So in 1971, Franz Wegener actually showed that, in fact, there is a duality, but the dual of the Ising model is not a magnet, but it's a theory with a local symmetry, with what we call a gauge symmetry. So it's a gauge theory with the same group, transformation group that the Ising mode uses, which is Z2. So we call it the Ising gauge theory, the Z2 gauge theory. In that case, in the case of the magnet, as you saw here, the interactions take place along the links of this lattice. In the case of the gauge theory, they take place along plaquettes of the lattice. And so there are 2 phases in that language, in that case, and the 2 phases correspond to the problem of confinement and deconfinement in gauge theory. So the analog of the low temperature phase that we had before is called the confining phase. And the analog of the order parameter of the Ising model is an object that condenses in that phase. So it has, we call it a disorder operator that actually condenses in that phase. Whereas the other phase actually looks like particles, essentially, as I said before. So if you take this loop and you think of this direction as time, then essentially here you can see a pair of particles that are created. In this case, there is no sense, there is no charge because it's of the nature of the Ising model. They evolve, they can actually create more, and so on and so forth, and then they destroy it. But in this other case, if you cut this at planes at constant so-called time in this direction, you can think of this as being some kind of string, closed string that is evolving, and then it evolves in time, and then it disappears. And this string actually has an energy per unit length because it has to span an area. So that's why it's confining. So this actually is a simple model of quark confinement. There are no quarks here. The symmetry group is wrong and all of that. But it's a simple version of that. And you can see that there is this duality that is present in this case. So in this case, the dual is not even the same theory. Okay, it's a theory with very different symmetries. In fact, if you look under hood, it turns out that the so-called deconfined phase that corresponds to this in the Ising model is this high temperature phase, but which is essentially perimeter-like, there are 2, of course. It turns out to be topological, which the Ising model doesn't see. And that's because you need to take into account the boundary conditions in the dual theory, which are non-trivial. So it turns out to be the simplest topological phase of things that we nowadays call topological phases. This is, in fact, the simplest topological phase, is the so-called deconfined phase of this theory. So duality, you can see it's mapping things with where the parameter I'm calling it the temperature, I can call it coupling constant, is weak in one regime and is strong in the other. When it's strong, it may be hard to understand. For one theory, then you do go to the dual, and you, if you're lucky, you can actually make some leeway into solving the problem. So this is one of the uses of duality. Okay. Okay, so in the quantum version, you can say, well, you can do the same thing if you have a spin chain. In fact, it's the same problem we just did before. So this is called an Ising mode in a transverse field, or the quantum Ising mode. It's essentially, this is the analog of the kinetic energy, analog of the potential energy. And you can also perform a duality transformation. You essentially show that the product of a pair of spins, say on these dots here, which are the sides of the original, you see in the one-dimensional chain, it's nice that the original lattice and the dual are essentially isomorphic. They are the same theory in a sense. And so you can construct an operator that creates kinks that flips spins from one point to the left. We call it tau 3 here. And tau 1 is essentially a product of the two sigma 3, is the product of the spins in the original theory. And these guys satisfy the same algebra that the spins themselves do. Okay, so, but then you find that this Hamiltonian, which has a coupling constant, after duality looks the same, looks identical, except that the coupling constant is in the wrong place. So strong coupling here is weak coupling here, and vice versa. And this story actually continues. It can be done in other cases. Okay, so in fact, if you go to 2 + 1 dimensions, as I said, which will be the case of the 3 + 1, 3 dimensions as we were doing before, it's the same story, but the dual, as I promised, lives on plaquettes. So here is the Dirac lattice, the black dots are in the Dirac lattice, the circles are in the dual lattice, and in the dual lattice, they live on plaquettes of the dual lattice. But this is a gauge theory, and so it has what is called a Gauss law, which is a generator of gauge transformations. So it maps equivalent states. And in this case, corresponds essentially to the product of these tau 1s at every site of this lattice. So people that have read probably Kitaev's work, this is sometimes called the star operator, but just simply the generator of gauge transformation. It's all that there is to it. Okay, so he plays a role, essentially this condition that the product is 1 is the analog of the statement that the divergence of the electric field is 0 in electromagnetism, in the absence of matter. So if you want to have matter in this case, or sorry, in this case, there will be some places where this will be -1. Okay, so there's another thing that is called duality. And this is also something that has a long history, which is mapping bosons to fermions, or it's called bosonization. Okay, it is a form of duality as well. This was discovered by many people and rediscovered by many others. It was discovered originally by Lieb, Schultz, and Mattis. Actually, Lieb and Mattis, back in 1964, I believe. And then it was rediscovered years later by Sidney Coleman and many others in the 1970s in the field theory literature. But it's the same concept. So in the original problem, what you have are fermions. These are relativistic fermions, Dirac fermions, that live essentially on a line. And so they move to the right or to the left, so they form a spinor. You can compute the densities and the currents, which are here. And they have this non-trivial algebra that says that the density and the current do not commute. And this is actually a non-trivial result. And this result goes back actually, Lieb and Mattis realized that this had to be the case. This is what actually in the field theory is called the Schwinger term. And it plays an important role in this concept, because you see now when you have two operators with commutator is almost a delta function, it's a derivative of a delta function, means that perhaps you can rewrite this in terms of some boson. But the boson is a boson, and the canonical momentum, we have non-trivial commutation relations. And so you do it by, say, you write the density in terms of the gradient of some field phi up to some coefficient, and the current in terms of this canonical momentum, which is essentially the time derivative of phi, again up to some coefficient and important sign. So with this provisos, this object, these two components, this current, which are these things, are conserved. So they satisfy a continuity equation. And you can write down a Hamiltonian for this problem, which is free. And this is free only in the absence of external free fields. But if you add an external electromagnetic field that couples to this, so what's the external electromagnetic field will do? Will induce some current, which will be, there will be, say, more right movers and left movers. The densities will become unequal to each other. That has the form of this equation here that is called the anomaly equation. So in this theory, as it stands, there is another current you can define by flipping J1 and J0 into another current called J5. And that current is, at least at the level of this naive construction, these currents appear to be separately conserved simultaneously, but not in the presence of a background field. So this is, I think nowadays it's called a 't Hooft anomaly for some reason, but this is just the axial anomaly of which has been known for a long time. And this object has a topological origin, this quantity, this particular combination. So the fact that this is actually violated, that this current is not truly conserved, for the reasons that I explained, proves that this boson actually is not really free, because the equation of motion, which is written here, is proportional really to the magnetic field, to the electric field. There is no magnetism in one dimension. And so in particular, if you compute what is the charge, in this case, you can show that if you add some charge to this particular system, essentially you need to change the boundary conditions of your scalar, of your field phi, in a manner which is proportional to the amount of charge. So it controls the charge. Periodic boundary conditions means you're in the vacuum state, there is no charge. If you add some charges, then you need to twist them. Okay? So this is actually all coming from here. So in this sense, you're mapping a system of fermions to a system of bosons, so vice versa. There's also an actual expression for the operators that create these fermions, or the fermion operators in terms of the bosons, but let me not get into that today. Okay, so let me go back to 3 dimensions, 2 space, 1 time. So I'm going to either think of this as 3 dimensions in statistical mechanics, or a problem in quantum mechanics or quantum field theory in 2 space and 1 time. Let me think of a problem where I have in the low temperature in the phase, I'm going to have some kind of superfluid, which has an order parameter which we call a complex, is a complex field. It has an amplitude and a phase. I will have a little more of that. In a system like that, you have excitations that look like vortex loops. So here is a vortex loop. So you can think, if I want to insist of calling this time, my vortex loops essentially, if I cut at some constant time here, it is as if you have a vortex and an anti-vortex separated at some distance, so they are created together and then they are destroyed. That's the meaning of this loop. On the other hand, I can go to the analog of my high temperature expansion that I did before, that also is a theory of loops, but they correspond to particles and now antiparticles, or holes, if you wish, created and then destroyed. The energetics, even though both are loops, the energetics is actually different. This one turns out to be an energy per unit length, as in the case before. This actually has a logarithmic part in it. Okay, so let me come to this problem. So the question then is, how do I find a theory that has these 2 types of phases that will play the role of the dual method? And this is an old problem that was of interest to many people. I don't know if I have a separate transparency to that now, here. Okay, so let me write this in the language of Lagrangians. So in one case, we have a 3-dimensional so-called XY model. An XY model is essentially a magnet where the spin or the local magnetization has to be in a plane. So it has to rotate. It's called a planar magnet or XY model. It's a model of a superfluid. And in field theory, this is called a complex scalar field. So a simple model that at least we can pictorially write down, this is the Lagrangian, has a term which has the gradient pieces here, couples to some background electromagnetic field through its covariant derivative. And then there will be various terms. Depending on the sign of this quantity I'm calling M square, I will be in the unbroken phase or in the broken symmetry phase. So if M square is positive, there is no expectation value for phi. And this is the symmetric phase. In condensed matter physics, this is usually called a boson is insulator. This is one of the terminologies that people use these days. Okay, it's not the same as this, well, okay, let's call it the boson insulator. It has word lines that are these excitations of phi that look like particles and holes, and these are these things. On the other hand, if M square becomes negative, these two terms fight each other. And then you can have a state where the expectation value of phi is not zero. This is essentially a superfluid state, it's a condensed. Okay? And so in that case, then you're going to have, that's where you have vortices, and they have vortices and anti-vortices forming loops. That's essentially the description I had before. So the question is, what is the dual of this theory? So the conjecture is that the dual of this theory will be such that these two pictures will be switched, but the interpretation then will be different. But it turns out that the dual of this theory is an old problem in statistical mechanics that people didn't know how to solve. It's a problem of what happens if you have a superconductor, it's in two space dimensions or 3 dimensions in this case, either at 0 temperature or at finite temperature, I can do it in 3 dimensions, coupled to a fluctuating electromagnetic field. And people did complicated calculations in 4 dimensions using the epsilon expansion and other things like that. And the prediction was that the transition will be a first-order transition, which nobody ever saw. And there are other systems that are mapped into this, and this first-order transition kept not showing up. So people didn't know what to do with that. And there were a number of people that were interested in this problem, particularly, well, there is a version in high energy physics of this. It's called the Coleman-Weinberg problem, which is essentially the same one. Okay. And what the people that actually solved this problem actually showed this duality, the duality works. So as you can see, it's a very similar theory, except that it has a dynamical gauge field, which is called little a. The sign of M square is flipped. So when this guy is in the expectation value 0, this guy will have an expectation value. And the coupling to the electromagnetic field is coming through this peculiar form that looks like A times the current, the curl of little a. So it's like a J dot A coupling, plus some sort of Maxwell term. Now, if this guy has an expectation value, the electromagnetic field, call it, this gauge field, will be Higgsed. And so it will actually become massive. And so these loops essentially are going to have an energy per unit length. So you will be in this phase. On the other hand, if the expectation value of phi is actually 0, then basically you're going to see an effective long-range interaction, because essentially this Maxwell-like term will kick in, and in 2 + 1 dimension, that's a logarithmic interaction. Okay, so the dual of this problem is essentially just that. And so this is actually a way of understanding why you can actually have a continuous phase transition in this problem, which was an elusive problem. So it was actually, this duality was discovered by several people, by Michael Peskin when he was still a student, by Mike Stone, my colleague, who was also a student independently, this is 1978, and by Dasgupta and Halperin in 1981. This particular version that I'm presenting here is essentially the Dasgupta-Halperin presentation, which is physically more transparent, in my opinion. Okay, so this is So you map, so there is an interesting mapping. So again, these are two different theories, as you can see. But the same expansions, the same loop expansions essentially can be used to justify them. Is it the time I have, or this is it? Okay, these type of arguments have recently been promoted to a large number of conjectured dualities that involve fermions to fermions, fermions to scalars, scalars to scalars, and they have become a web of that. The original calculations that actually motivated, okay, except for this the problem I just discussed here, much of this actually is from about, I would say, 6 or 7 years ago. Different groups, mostly working in non-abelian gauge theories with John Simon's terms in the large N limit, essentially including people like the past director of this institution. Spenta was involved in that, and various other people, Aharoni Ofer Aharoni in Israel, various people actually worked on this problem. And there are various dualities that people conjecture. For instance, the fermionic particle vortex duality maps fermions to fermions was conjectured by Son as a way to explain something we call the compressible state of the fractional quantum Hall effect. This is a quantum Hall effect where the quantum Hall effect doesn't happen. Okay, so where the system loses the gap. And most of you were in the lecture before. It was briefly discussed by Genpati. So Son actually made a bold assumption that maybe the best way to think about this problem is some sort of Dirac fermion coupled to some gauge field. And then was the same ideas actually for other reasons were actually put forth by Mark Smetlitsky and Ashwin Vishwanath in the context of three-dimensional topological insulator. So in this case, it's the same story. You map time reversal invariance or time reversal transformation to charge conjugation, and it maps essentially the magnetic field to a chemical potential. And so it is electromagnetic duality because it maps electric charges to magnetic charges. Okay, so you can see that this is at work here too. And there is a bosonization duality. And in this particular form, it was put forth by Seiberg, Sentil, Wang, and Witten. And this was essentially, they took the large N theories that they knew about from the string theory literature and boldly said if it is valid for large N, it's valid for N equals 1. Okay, so who knows? I'm not going to, in fact, with a student of mine, Hart Goldman, we actually have a proof. It's a physicist proof of this based on loop models. So I always like to recall that Elliott Libb, who's a famous mathematical physicist, said that mathematicians prove things rigorously, whereas physicists prove things vigorously. So this is a vigorous proof, okay? Okay. So essentially we show that the two expansions actually map into each other. What happens precisely at the critical point is something we cannot say, but we could map the operators in the two phases, and with that we essentially quit. Interestingly enough, you map a problem here of bosons, which are scalars, to a problem of spinors. So notice that these are not just any other fermion, these are Dirac fermions, and they are spinors. So this is consistent with the spin statistics theorem, and that's non-trivial. So to prove that with Goldman, we had to do quite a bit of work to understand how that was going to turn out. Okay, so it's a paper. Not many people actually read that paper. It doesn't have many citations, but it's a paper I love. Okay, some of the papers I love are the ones I have very few citations. Okay. It's another form of duality that the string theories actually created. Essentially, this is the work of Maldacena and many others. It's in the context of string theory and quantum gravity. So it's called, usually it goes under the name of the ADS-CFT correspondence or the gauge gravity duality. There are many names to this. So the idea here is that it maps two theories. one theory that lives, so this is like a renormalization group transformation. You begin with a theory with a very small cutoff, as we call it, and then you begin to coarse grain the theory more and more as you go from the short distance regime, so-called ultraviolet, to the infrared. And what these people boldly showed, that at least in certain classes of string theories in the classical limit, the dual lived actually at the boundary of a space, which is called ADS. So here it is. So Maldacena calls this a spherical, the hyperbolic curve approximation to physics. You know, the spherical curve approximation is a common approximation we all use. Okay, this I actually took that from a paper by Maldacena and Klebanov, actually. I like this picture of the ADS space. And so it's the same story. The boundary is here in the ultraviolet, and in the infrared, you solve some problem in gravity, and then you relate the solution of these classical equations of gravity with some additional fields to properties of what is actually a conformal field theory at the boundary. It's actually a theory as some kind of critical point, but it's strongly coupled. Okay, let me turn to the fractional Hall effect, okay, which is partly the subject of this meeting in the school in particular. So I'm going to do a lightning review of what our organizer has done in many talks. So, but since there are people here that haven't been in these talks, I want to go very quickly. So this is a problem of electrons that live in 2 dimensions. These are non-relativistic in Landau levels created by a large uniform magnetic field. And we're going to assume that it has a certain number of fluxes, like quanta. And you measure the density there, not in terms of the areal density, but of the fractional occupancy of a Landau level. So we call that the filling fraction, which is the number of electrons divided by a number of fluxes. It turns out that this was known experimentally. It has a quantized Hall conductivity in terms of fractions. Okay, so it's quantized in terms of fractions, so it's not what you normally call quantized. But these identifications in particular, these values are very precise, in particular in the integer case that corresponds to n equals 0 in this picture here. The quantum Hall effect, as it is called, is so precise, like this is known in 1 part of 10 to the 9th or something like that, that in fact is both the standard of resistance is now uses the quantum Hall effect, but it's also the most precise determination of the fine structure constant. Comes entirely from here. That's because of these quantization properties. So this is rather peculiar where you get these precise fractions. So this led to a conjecture by Laughlin, or proposal, that this is some sort of a quantum fluid, which was uniform, whose wave function looks something like this. This was inspired somehow by properties of the wave functions of liquid helium for a superfluid. That's how he came to this. But this related, so this is so-called Jastrow factor, which is here. And this exponential factor, which essentially makes things convergent, this is due to all of this is due to the fact that you work in the lowest Landau level. Here, Z is a complex coordinate, is x plus iy. Now, about the same time, this is 1983, when Laughlin wrote this. A little earlier, there was a proposal by Wilczek that charge flux components, composites, will actually produce something which we call statistical transmutation, or something called anyons. These are ideas that other people have proposed before, in particular Leinas and Meerheim and others. So there are various incarnations of this. But the actual physical incarnation is in the quantum Hall effect, in the fractional Hall effect. And so the first field theory of this essentially was something called composite bosons, in which essentially you attach a number of fluxes to bosons to essentially become fermions. This was done by Jean Hansen and Kuvelson, and also in a more obscure way by Nick Reed. This was in 1989. In 1991, with my former student, Ana Lopez, we gave an explanation of the sequence of states which were actually proposed by Jainendra Jain, which are generalizations of these Laplace wave functions. And these are the most prominent states that are seen in experiment. And Jainendra's work, numerical work, essentially explains, quotation marks, why these states are more prominent. We gave sort of a field theoretic version of this. Now, all of these theories involve something called the Chern-Simons term. It's a gauge field in 2+1 dimensions, so it says 3 components, so it has 3 space, it's time and 2 components in space. So it's a vector field with whose action it looks peculiar. This doesn't look like electromagnetism because it's first order in time derivatives. So why is first order in time derivatives? Because if you have an action which is first order in time derivatives and you change the sign of time, then it changes sign. So it's odd under time reversal. It's also odd under parity, which in 2 dimensions is a reflection symmetry. And so this is the only term that you can write, in fact, that is actually invariant under this, well, it has this physics, it's odd under time reversal and odd under parity. And it turns out that for topological reasons, the prefactor here has to be quantized. If you put this not on a plane, but on a torus or on a sphere, it turns out due to the so-called large gauge transformations, this number has to be quantized. Otherwise, the theory is inconsistent. And if you have essentially some current essentially associated, you couple this to that, you find that this simple Lagrangian actually encodes 2 different physical effects. If you expand this out, there are terms that involve the time derivatives and terms that don't involve the time, involve only the space derivatives, so it's like a curl. That term essentially gives you a constraint that relates the charge density to the flux with a prefactor that precisely involves this factor of m. Whereas the other term that involves the time derivatives gives you the commutation relations, and the commutation relations are peculiar. It tells you that the commutation relation of this vector potential along the x direction and in y direction, they don't commute to each other. Okay, and this term is very important to get what is called the degeneracy, the topological structure of the theory is really very important. These commutation relations are essential. So this theory, all of these theories, both the so-called composite boson theory, the composite fermion theory, at least in the field theory language, they all involve this type of gauge fields. So the composite boson looks something like this, and let me do this very quickly because it's a very busy slide. So there is a covariant derivative that has the external electromagnetic field and something that people call the statistical gauge field. We heard today about this. Okay. And so notice that I have a term here. I have actually something which is not allowed. Notice I have my m in the denominator here. As it stands, this theory is not consistent on a closed manifold, but I can add another field and put this in the right place. I know how to do that correctly. So this is a theory. You map the theory of electrons with density-density interactions to a theory of bosons. You notice it's field phi, density-density, and this is non-relativistic. Notice that you have a first-order time derivative here, but there are 2 second-order, there are 2 derivatives here. Okay, so if you assume, and this is actually what these people did, Jan Hansen and Kivelson, that there is a complete cancellation, at least on the expectation value of the external field, then in a sense, this boson that is here doesn't see an electromagnetic field, and it will condense. And when it condenses, you say, well, you can split into an amplitude and a phase, and you can compute essentially how much, what the amplitude is, knowing what the density is, and you find that, in fact, the density is such that the filling fraction is precisely this quantity, 1/m. The quantity I'll note here is the only scale in the problem, and is called the magnetic length. So these are precisely the Laplace states in this picture. Do a little bit more work, and you compute the fluctuations, and if you integrate them out, then you find two things. One, that the response to an external electromagnetic field is such that you get precisely the value of the conductance that you expect, 1/m times E²/h. But you can also, this being a complex field, the field phi will actually have vortices, much like the vortices I discussed before. And what is a vortex? Is something whose phase essentially winds in a closed loop by 2π times an integer. So here is the vortex, a classical vortex solution, and the circulation of this vector potential is plus or minus 2π. If you use this and you calculate how much charge is associated with this vorticity, why is there a charge? Because there will be a curl associated with the center of the vortex. You will have some flux, and there is a relation between flux and charge, as I showed you, and therefore that means that the charge can be computed here essentially using the circulation, and you get this precisely is plus or minus E/m, depending whether it's a vortex or an n-type. Okay. Now, if you do a bit more, it turns out that these vortices are not actually bosons. They are what we call anyons. And you see that in the following way. So if you use this identity that I have my Chern-Simons term plus another term like that, and you integrate out, say, for instance, the field B, then you get essentially, this is like a Gaussian identity. So the Gaussian term, this term essentially gets flipped and has a minus sign. It's as in the usual Gaussian integral. So you can go to this other picture, which I wrote here. This was formulated by Xiaogang Wen. And this field, little field B, now is called a topological or the hydrodynamic field, and it contains all the topological structure of this theory. The current here, JV, these are the vortices precisely, or the world lines of the vortices are represented by currents, and the coupling to the electromagnetic probe field is here. Notice that this is nothing but a curl. So we recover the correct conductivity and fractional charge. But if you now integrate out the field little b, and you calculate what is the form of the effective action of these currents, you find that it has this non-local form. Turns out that if you now say that the currents essentially are non-zero only along these loops associated with the world lines of the vortices, this is nothing but the so-called Gaussian variant that you use to calculate the number of times you have to wind when you make a transformer. Okay, so it's to compute the self-inductance in the transformer, use an expression which is similar to this. But it has this factor of π/m in front. And so this actually produces precisely the fractional statistics associated with the states. This is actually how you prove that these excitations, these vortices, are actually objects that not only carry fractional charge, but carry fractional statistics. And this is a very deep concept, because we were taught in kindergarten that there are only two types of things, bosons and fermions. Okay, and this is true coming from local field theory and other arguments in 3 dimensions, 3 + 1 dimensions, but in 2 dimensions, you have this additional form of statistics. What is the meaning of statistics in this language? Statistics here means if these are the world lines of these objects, of these vortices, you can braid them. So you can make essentially transformations where they exchange their positions without crossing. And this is very important. Otherwise, this doesn't make any sense. So it's important that they don't cross. So the configurations of my vortex lines essentially correspond to braids, as you can see. And the braids actually form a so-called group called the braid group. The first calculation that proved that these things were vortices was done by Jarova, Schrieffer, and Wilczek, where they use a quasi-static argument, essentially, an adiabatic process to do that. It had been proposed also by Halperin, looking at the structure of the wave functions, but this is a more direct way in the sense that uses precisely the very phase in an essential way. Now, it turns out that, I will see in a moment, that there is a more exotic form of fractional statistics called non-abelian. fractional statistics, which is of great interest for making the possible best ever qubit that anyone will ever find, but no one has ever been able to construct until now. Okay. So let me come to this. So these vortices, as I said, I can transport one around the other. This is equivalent to this during these exchanges. These are the cutting in time on a given time surface. So it's equivalent to take the wave functions of A and the wave function of B. And if I transport B around A in a full braid, a full loop, then it will carry some phase. Notice that I go back to A and B, and the phase is 2 pi over n. If you do a half braid, which is an actual exchange, then you get pi over n. So you can write this in terms of an operator that creates vortex A, an operator that creates vortex B. You can do something else. You can also take A and make it very close to B and look at it from far away. Then it will look like a vortex of twice a charge, or the twice a winding number. And so it will have essentially a value of this quantity theta multiplied by a factor of 2. So in fact, if you have one with charge n and one with charge n prime, from a distance, it looks like something with n plus n prime, but this is only defined because it's up in a phase factor modulo m. So there's a finite number of these objects. So this process is called fusion, and it's sort of the flip side of the braiding. Okay, so some proposals for studying essentially topological quantum computing essentially involve either braiding or fusion or both. Okay. So for Laughlin, you have particles therefore which have charge E over n times n, and they are defined, there are m possible versions of this. And similarly, the statistics is n pi over n. This is for the simple abelian states. Okay, there are things called the non-abelian, and this is what I'm going to close with this. I can take a few more minutes from your talk, right? So there are other kinds of vortices where called the non-abelian anyons. And you see, until now, what I said is, well, they carry a phase, and then I look at how things wind. So I assume that all of the properties of these vortices are entirely understood once you know where they are. You're going to see in the non-abelian case that this is not the case. So a state that is very popular is called the Moore-Reed state. It's very similar to these Laughlin states. It has this Pfaffian factor. And because of the Pfaffian factor, the particles tend to be closer to each other because it looks like a pole. It's not really a pole because it's canceled by these guys. But essentially, it has a Pfaffian in it. And it turns out this has an interpretation. There is some kind of pairing going on in the system. That's at least an interpretation of what the Pfaffian means. They have filling fraction, which is 1 over n. For this to be a good wave function for a fermion, this is odd under exchange. Therefore, n has to be even for fermions. And so this, you get the wave function, which is properly antisymmetric. If n is odd, then this will be even, and so will be a theory of bosons, a wave function for bosons. So a candidate, there is a fractional quantum Hall state that has been studied since 1989, and is very mysterious. There is very little we know about this state. We know more than before, but not enough. At filling fraction 5/2, that means it's in the first Landau level, not in the lowest. You fully fill the lowest Landau level with up and down electrons, and up and down spins of the electrons, and half filled and fully polarized in the first Landau level. Okay, there we go. Okay, so this so this looks like nu is 1/2, and this is 1/2. It's supposed to represent that. Now it turns out you can actually you can create the analog of holes in this problem, or these vortices, the analog of the vortices I discussed before. But they have a peculiar property. Suppose I have 4 of them. With 2 of them, you cannot tell the difference. It turns out that the state of these 4 vortices is not fully specified by the coordinates. The reason being that when I include the vortices, the wave function has branch cuts now, and there are different ways of running the branch cuts. And there are only two linearly independent states that you can construct, and let me call them 1 and 2. So if I braid, say, A and B, 1 essentially will go into a linear combination of 1 and 2, and the same is true for the other processes. And that requires a matrix. It's not just a phase, but a matrix of phases. And so different, if I have a large connection of these anyons and I try to braid one and the other, then you're going to have different matrices, and these matrices, being matrices, they won't commute in general. So that's the non-abelian character of this. Now notice that this is a two-state system. Okay? There are two states. So it's called, in that sense, it looks like a qubit. But the character of this qubit is different, like a spin. It doesn't belong to any one of these anyons, belongs to all of them. So it's a very non-local object. The state is not localized on the coordinates, in other words. So it's not an internal degree of freedom of this object anymore. Okay? It's topological in nature, and it's so well protected that it will be very hard to understand what it does, because you have to do something to measure it. Okay? Now, how do we measure fractional statistics? People have made some, after a long period of many efforts, there has been some recent progress in this about how to detect anyons. The way you do this is by essentially making what is called a quantum interferometer. This is an analog of the familiar Fabry-Perot interferometer used for light. Essentially, this is a quantum Hall fluid. These are these edge states. And you have this quantum point context that makes these narrow constrictions here that produces tunneling. And this, because there may be some of these anyons sitting here inside, these different processes don't commute, and they have a non-trivial phase factor. And so you see both an Aharonov phase, but you also see, more importantly, the fractional statistics. This was proposed by Chamon and many collaborators in 1997 in a paper that I wrote with Nayak, Wilczek, and Cvelik in 1998. We proposed the analog of this for the non-abelian states. We thought that nobody was ever going to do an experiment, so we never cared to actually do a prediction for a particular state, which is the case of nu equals a half. This was, but thanks to Microsoft, back in 2006, people actually began to try to make these experiments, in particular Willett. It has been trying to do this. It's a very hard experiment, and it's still not conclusive, in my opinion. So many of these things were rediscovered afterward by various people, including Kitaev and Stengel, and Halperin and Adi Stern, back in 2006, which essentially we had a version, the general algorithm here in our paper, but they did the case that actually mattered for, they actually matter for the nu equals a half case. Now, very recently, so this is still out there in the case for the non-abelian cases. I don't think this is the dust has settled, and no one has ever proven this. But for the case of the abelian state, people try to do this quantum interferometer. This is one particular picture from Manfred's group from 2020, where they actually saw this 1/3 state. It actually measures not the exchange statistics, but the double, twice that, a full braid, not a half braid. So it measures, you get essentially 2 pi over 3, not pi over 3. Okay. But that's good enough for me. There is an alternative to this in using the so-called collider experiments, and we heard a beautiful talk yesterday about that, which essentially using noise experiments that basically gets to the same physics, essentially. So, and there is a third class of interferometers. This is the Max Zender by Moti Heiblom. Moti has been doing this for a long time and has now made it work. So there are 3 types of experiments that actually confirm this. There's a non-trivial check here, is to go to the next state, which is 2/5 in the Jane sequence, because it turns out that it has a more complex structure And there are more knobs you can check essentially to make sure that you're actually measuring. So for instance, you're supposed to get a charge which is 1/5 and not 2/5. And the statistics is not 2/5 or 1/5, it's some other number which I don't care at the moment, but that's actually what they measure. So these are important checks, and these are very recent things. Now, if one could do this for the non-abelian case, then one will have what is called a topological qubit at one's hands. Okay, so it's a very exciting problem. You can do with cutting-edge technology. These are the cleanest semiconductors they exist. They have mean free paths of the order of a tenth of a millimeter or something like that, at least a nominal one. You can see it. These are ping pong balls going around, essentially, if you want. At the same time, you are doing fundamental science. Whether people can do computation with that, okay, it's good for them. I congratulate them. I'm interested in the physics. Okay, that's my job. Okay, let me skip this. Okay, I don't have time. Okay, there is actually something here I wanted to say. So there are these compressible states that exist. So this is a trace of the whole resistance and the longitudinal resistance function of magnetic field. There are lots of fractions, including the J states, and there are these compressible states at 1/2, 1/4, and so on. So there are many states of this type. This has been known for a long time, but there was an experiment back in the mid-90s by Shahar and company. This is in Dan Sui's lab. This is nu equals 1/4, so it's not the 1/2 compressible state at 1/4. And they saw a peculiar result that the current as a function of voltage changed as they went from the so-called insulating regime into the fractional regime. So essentially, and it looked like in one phase, the current and the voltage get exchanged as you go to the other phase. So there is a symmetry in these IV curves. So it looks like charge and current, so current and voltage get flipped. And this is what you expect if you exchange electric charge with magnetic charge. And so they conjectured, actually with Sondi and Shimshwani, so there was a conjecture that there was some kind of self-duality at this phase transition. There's some kind of self-duality at work. And in fact, this was something that we couldn't, nobody had a proof of that. And recently with my student, Goldman, back actually 2 years ago, using this web of dualities, we actually proved that in fact in 1/4, in fact, in all of these compressible states, you have essentially an effective self-duality. Okay, the conclusions are the duality plays a key role in understanding many problems, many areas of physics, ranging from stat-mech to field theory and string theory, including perhaps gravity, I don't know. Strongly interacting theories are mapped into generally different, weakly coupled ones. It's an indispensable tool for understanding systems without the use of perturbation theory. If you use perturbation theory is only interesting when it fails. Okay, when it works, it's just more of the same. Okay, when it fails means you have the wrong vacuum. Okay, so here is a case where you can actually solve a problem that you don't know how to solve by mapping into another problem that perhaps you know how to solve. Okay, that's the strategy here. So it provides actually for novel ways of understanding new mechanisms for phase transitions. For instance, vortex proliferation, condensation of monopoles, etc. And there are deep connections between duality and geometry, as I mentioned as I went along. And okay, this is it. You're the chair. Yes. One's the chair, over the chair. Yes.
Hello?
A question here.
Is it on?
There is a question by.
Okay. So Yes, you are.
You mentioned the duality in the context of bosonization in 1+1 dimension.
Yes.
Now, this, of course, is heavily used to describe not the bulk, but the edge
Yes,
of
that
one
too.
whole,
Yes,
except that you have to geographically separate
right,
the two counter-propagating chirals.
correct.
So when you have these chirals,
Yes.
each of them, there is a chiral anomaly. Does it modify the
No,
argument?
because there is an intervening bulk. In the middle between these two guys, there is the bulk. And the bulk has what is called, so a chiral fermion, or a chiral boson actually, has what is called a gauge anomaly. It's not gauge invariant. Neither is the bulk if you actually cut it at the edge, because its charge goes in and out. So there is this boundary to bulk correspondence. And so because the bulk is incompressible, the anomaly of one edge gets transmitted to the anomaly, cancels the one of the other edge.
Oh, sure, of course, but
Yes.
that's obvious. But
Yes.
my question is whether the original theory separates geographically into two counter-propagating
Right.
chirals.
Yes.
Does the dual theory also separate
Yeah.
geographically?
Well, duality here is more the duality between the bulk and the boundary. There's no other duality in this other case. In the case of Chern-Simons, in some sense, it's a self-dual theory, Chern-Simons. As you saw, it takes M to one over M, okay? It's the same theory.
So you cannot take just the 1+1, the bosonization in 1+1 dimension, and the duality there.
No, you cannot do that. No one is chiral. No, it's because it cannot. It's essentially essential to think about it as a boundary of the bulk. It doesn't. It's a theory. It doesn't exist on its own. It's the same problem with these topological insulators that you in 3 dimensions. That there is a boundary state. There is an anomaly there too, which is cancelled by the other boundaries at the opposite surface. So the axial anomaly on the one-dimensional problem becomes what is called the anomaly in flow. It's a flow anomaly from one surface to the other surface. And the same is true in these quantum Hall states. Yes, Mike. Yes.
Okay, so I want to get your thoughts about the following. So you said that there are many things that are called duality, right?
Yes.
And you went through a set of examples. the
Yeah.
electromagnetic
It's not exhaustive.
Okay, of course not, of course not. But here is my question. So if you look at electromagnetic duality, you look at the, Kramers and Wannier duality, you look at, the duality for the transverse Ising model, whatever. It's clearly that this is an isometry. Mathematically, it's an isometry. So that means that you can map, one from the other through an isometry, essentially. So
For that to be an isometry, you have to tell me how you measure the metric of isometry.
no. Isometry, I mean, if you map a model of a certain dimension, for example, the Kramers and Wannier for the Ising model,
Yeah.
I mean, clearly you go from the same dimension to the same dimension. That's a unitary operator. I mean, it's a usual unitary. Okay.
It's not a unitary transformation.
Yes, it's a unitary
No,
operator.
it's not. Kramers and Wannier is not unitary.
It's unitary.
Okay.
Kramers and Wannier
Okay. No, it's not.
is unitary.
No, it's
you
not.
can read.
Okay.
You can read my papers, and I will show you how you do it. Okay. Now.
Yeah,
No. But I want to get you thinking about the following thing.
Yeah.
So the other dualities, like the web of dualities,
Yes.
okay, that's not an isometry in any possible way. It's just some conjecture about mappings of operators. Okay, so it's not the same thing.
It is the same thing.
No, it's not the same thing. Okay.
Well, Gerardo,
So-
we'll talk about this later. Okay.
Yeah, okay, we can talk. No, but I could like to get your thinking about that, because you see, you are calling the same thing two things that mathematically are not identical.
Well,
Okay,
I'm a
so-
physicist. Okay.
Sorry?
I am a physicist.
But it's not the question about physics. It's not a question about
Look,
physics.
it's a vigorous identity. Okay. So let me put it this way. It is, in a sense, it's electromagnetic duality is at the root of this web of dualities. Except in addition to that, it map fields with different character. Okay. But the same is true with the Ising model in 3 dimensions. It maps to a gauge theory, which is a different kind of theory, with different character, but they are still dual to each other.
Exactly.
It's not the same theory.
It's not no, but duality is not self-duality. I mean, there are models that you can do. The model basically maps essentially to the same model, but essentially with the reshuffling of the coupling constant. That is self-duality. Now, the case of the 3-dimensional model, you go to a different theory, as Wegner showed. Okay, and that's a duality. It's not a self-duality, but it still is an isometry. So that Wegner thing is an isometry, but it's not true in the web of dualities.
Okay, we'll discuss that later.
Okay.
Other questions?
Hi, thanks very much. In the new equal to 5/2 state, where you have this qubit and the SU2 non-abelian enyon, I was just wondering, just as a general question, in these experiments, can you realize various unitaries by this braiding operation?
Okay, so this is the problem with 5/2. With this particular state, is not, how to say, is not universal. So these qubits are not, the type of unitaries you can get do not cover the Bloch sphere uniformly. The only version, so this is connected to a gauge theory called John Simons at SU2 level 2. There is a version that corresponds to SU2 level 3. It's called the Reed-Rezai state. This is a candidate for a state where a plateau that is seen at 12/5, but the only thing we know about that plateau is that the plateau exists. There's no other information at the moment. So if we believe it's a non-abelian state, the most likely candidate is this Reed-Rezai state, which is connected with the Chern-Simons theory SU2 at level 3. That theory has many enyons. It has like 5 different enyons. I forgot how many. One of them is called the Fibonacci n. And it was proven by Michael Friedman and others, mathematicians, that if you have Larson and Wang, and Zenger and Wang, yes. Okay, they proved that in that case, you can actually make gates, unitary gates that will cover uniformly the Bloch sphere. So the gold standard of this field is to get to the Fibonacci, which is not accidentally the gold standard because it's related to the golden mean. So that's what we want. But okay, I will be happy even to have the first.
Do you have a question?
Yes. Yes.
I would really like to have questions from the students.
Yes.
Sitting in the back. After Bern,
Yes. How about faculty members who are hiding among the students?
Thanks for the very nice talk. I believe on one of your slides, the boson field, there was a negative coupling, negative p-factor of the 5 to the 4 term. So is this for real?
No, not a 5 to the 4. Oh no, because this is not in Minkowski space-time.
Okay.
So you remember the Lagrangian is T minus V.
Okay.
That's why there are minus signs.
Okay.
It's not done in, I didn't write it in imaginary time, it's done in real time.
Okay.
Sorry, I should have explained that.
all right, I really want a question from a student. Eduardo, I think you should ask them some questions now.
No, I'm not you, okay. I can ask you a question.
Okay, even a postdoc, I'm lowering my standards.
Either I lost everybody or.
Oh, excellent.
Okay, good.
So for the case of abelian anion, the Berry phase that comes in as the abelian Berry phase. So we can do interferometry to observe them in an experiment.
Yes.
But for a non-abelian anion, what much that can get reflected in that interferometry?
Yes, and the reason is the following. So let me come to that picture. Now I have it. There we go. What we showed in this paper is the following, that, okay, so the way this works is you inject current here, the current gets split, and then there are these two different tunneling processes and the current comes out. And so you see an interference part of the current. There's an oscillatory component that you measure. So that's actually what the measurement is, okay? Let me continue. So it turns out that if you have some of these anions here, which are non-abelian, then the guy that will tunnel here will be one of them. So they're going to braid or fuse, which is the same. And then you're going to get various components. It turns out that the expectation value of the piece of the oscillatory part can be mapped to the expectation value of a set of what are called Wilson loops in Chern-Simons, the non-abelian Chern-Simons theory. And there is an algebra that essentially tells you how to compute these things. By the way, this is the solution of this problem is called maps into something called the Jones polynomial in topology, and this is the reason why Witten got not the Nobel Prize, the Fields Medal. Okay, so it turns out that we actually gave an algorithm using an algebra that was worked out by Verlinde that essentially tells you how to compute this interference component. In the case of the phi-half state, it turns out that there is an even-odd effect. Our complicated, more complex algorithm reduces just to an even-odd effect that in principle will be the smoking gun. The difficulty in practice is that there are also abelian anions in this state. And so the abelian anions, they mar this even-odd effect in making the interpretation more complicated. And in the 12-fifth state that I just said, could actually has Fibonacci anion there, there are many other anions, and so even the manipulation will be more difficult. So one of the things that I worked on recently is a proposal for a fractional quantum Hall state that has only one anion, and the anion is a Fibonacci. Now, it's a very special proposal. It's a theory of bosons, so it's doesn't quite apply to anything that any experiment can do at the moment. But if one could do that, that will be the state one wants. The other states are very interesting from our point of view. They are great, but from a practical point of view, they are very difficult to operate because of the additional components that will be very hard to disentangle, in my opinion. Maybe I tend to be too negative, but I should be more positive. Do you agree with me? I think you agree with me.
I have a bit of a tough question. We saw today a few kinds of dualities. For example, the Ising duality, the 2D Ising or 1D transverse field, is an operator kind of duality. You map operators to operators, you map a Hilbert space to the Hilbert space. And then there are other examples, like when you integrate something out in the path integral and you just go to a different theory. For example, you wrote Chern-Simons and then you added the vortex statistical field, and then you said, I can conclude something that vortices are anions. But when I integrate something out in a path integral, or on the other hand, I add some degrees of freedom, I change the number of degrees of freedom. I do not necessarily map Hilbert spaces. I may map correlation function. So if I want to calculate something specific, it's a useful instrument. But my question is,
but in the duality, you don't integrate out. You map states, map states to states, operators to operators, and processes to processes. By the way, the path integral is just as good as the Hamiltonian picture, quantum mechanics. Okay? They're complementary to each other. And so, for instance, the two-dimensional Ising model, the way it's usually presented, you can think of it as a path integral picture of the quantum version. Of the quantum version, using the transfer matrix, there is a relation between these two problems. They are not distinct. Okay.
So you're saying even when you talk about duality in the field theory language, you really map all degrees of freedom to all degrees of freedom.
You map all the observables. You map the observables of one theory to the observables of the other theory. You map the partition function of one theory to the partition function of the other theory.
And can you go back to the slide with vortices with the B statistical field? Where you had inverse Laplacian.
Sorry, which one?
Here, this one.
Yeah.
So
this is just a computation. If I want to compute an observable, you have to compute a trace, right?
Okay.
So integrating things out means computing a trace.
Mm-hmm.
So here I want to understand what are the quantum numbers associated with vortex lines. And so I need to trace over the degrees of freedom of my theory. And this tells me that the effective action of that has these phase factors that tells me that they have fractional statistics.
Okay, so
this
slide does not actually represent a duality. It just
this is a
computation.
It's a calculation, not duality.
Okay, so duality by definition is always mapping degrees of freedom one-to-one exactly.
So for instance, in the context of this bosonic version of the quantum Hall effect, you go from one plateau to the other using a duality transformation, because they correspond to condensing a class of vortices. Okay, and they represent that by making a duality transformation. So there are many uses of this.
Okay.
But in order, when you calculate, you trace over the degrees of freedom. That's how you calculate.
Yeah, the calculation. I got confused by this. I looked
so this is not a duality.
at the
this
first
is
identity, which has B field on the left and doesn't have it on the right.
Yeah, this is because, so here I traced over the B field, and then you get a theory on the A field that looks like that. It says that I can have a theory which is like a Chern-Simons term with a coefficient m to one where the coefficient is -1/m. They are related. This is like a Gaussian integral that is very similar.
I'm familiar with the calculation.
Okay.
Okay. Thank you. Thank you.
So this is an equivalence.
Clarifies
These two theories are equivalent. That's what I say.
Thanks a lot.
Brave enough to ask questions?
Hi, sir. Hello. Here. So I want to ask about like how duality is useful in characterizing these phase tensions, and also what is the connection between, you have mentioned in the conclusion, there's a connection between geometry and duality.
Between
Geometry
what?
and duality.
Okay, geometry and duality is essentially the electromagnetic duality is an example of that. It's what is called a duality of forms. In the sense of, for instance, a current is a vector field, right? So if you are in 3 dimensions, it's dual to an object which is an anti-symmetric tensor in 3 dimensions. Essentially, you go from D minus and on the lattice is essentially the statement that if you have a theory defined on links, the dual is defined on plaquettes on the opposite lattice. So they are dual in that sense. Okay. So it's a duality of the crystal, if you wish. It's a duality of lattices, which is essentially the duality of forms also. That's one aspect of the problem. Duality on its own doesn't solve the problem for you. Even if the theory is self-dual, to solve the problem is typically very difficult. In the case of the Ising model in 2 dimensions, it turns out that the self-dual theory is a theory of free Majorana fermions, and we know how to solve that theory. But even there, to compute the correlation functions is non-trivial, except for the fermions. There are other theories, for instance, in 2 dimensions, the 3-state clock model or Potts model, that are self-dual also, but they are also only nobody really knows how to solve this theory except at the critical point. And so to compute the correlation functions in general is hard. And in the cases of the theories that I presented, one really doesn't know what the critical theory is in detail. In the case of the 5⁴ theory with the scalar field, we know how to do it. We know how to compute the exponents with great accuracy. Is essentially the theory of the superfluid transition. So the precision of the calculations at the moment is so great that you cannot, that it's a limiting factor in the experiments is because you have gravity. So the experiment that actually checked the best calculations was done at the space station. As far as I know, that's the only science that came out of the space station. Sorry, this is my own take on that, but it's essentially because there's a very precise estimate of the critical exponents. And we don't have an exact solution of that, and we probably never will. Those are not integrable theories. And we have essentially various expansion methods and numerical methods, which are very precise, and we know how to characterize. Yes?
Sharon had a question.
No, just
Yes.
following up on Kirillo's comment and question. So you said duality means that you have to map state to state and so on.
Yes.
So then I was just thinking of this in quantum Hall. If
Yes.
you have a constriction, and
Yes.
if I think of a single droplet which has certain topological constraints. Now, if I go to so there is this strong quasi-particle backscattering and weak electron tunneling
There
duality,
it is.
right?
There it is.
Absolutely.
Yes.
So now the constraints are very different. The topological constraint itself, 2 droplet versus 1 droplet is very different.
Yes.
Now, if I have to do a Hilbert space level mapping, how do I do it between the duals?
Well, it turns out that this problem is.
One has to be careful, right? It's very different than having a Luttinger wire and having a duality between the weak backscattering, strong backscattering.
Yeah, but
element.
here is the same, because in a sense, this is a set of measure 0, and there is a flow among the set of measure 0 that you're looking at.
That's correct, but the global constraints are different. For example,
Yes.
the fact that you are
The fact that you mean about the fact that you split the fluid in two?
Yes, absolutely.
Yeah.
Splitting the fluid, and that's why there is an argument.
Well,
that-
okay, they are never fully split unless you go to the extreme fixed points.
That's true.
Otherwise, there is always some degree of entanglement between them, which
I
is
see.
always present.
So I think one has to be very
Yes, sir.
careful while really reconstructing this Hilbert space mapping then,
Correct.
because
I
the
know.
2 droplets have to be entangled in some sense
Yes.
appropriately.
So is
that
this flow
I get
that
the
I
right
have here?
physics.
So if you actually at the extreme ends of the flow, then you have some of these paradoxes.
So it's
Yes.
not an equal footing with Luttinger wire, I think,
Yeah, okay.
in this sense. I mean, yeah.
Maybe, I don't know. Red shirt.
Maybe I saw something wrong, but in one of the slides you skipped, I saw the fractional quantum Hall effect has some SL2Z. So, I mean,
Yes.
is there electromagnetic duality in fractional quantum
Yes,
Hall?
it's related. Yeah, this is what I mentioned before, that if you want to go from one plateau to the other, to explain the transition from one plateau to the other in this bosonic picture, you say that there is a set of vortices that condense. And the way you explain the condensation is by a duality transformation. So there is a duality. And there is an additional transformation that you can make that people call adding Landau levels. That says that if you work in the lowest Landau level, the first Landau level, the physics is the same. It turns out that these 2 processes do not commute, and they generate this infinite discrete group called the SL2Z. It explains many of the topological aspect of the topology of the phase diagram that is seen. Okay, now there is no real proof that SL2Z is actually inherent to this. It's a qualitative statement.
Just to follow up, any reason it's not SL2C? I mean, why is
Z.
it? Yeah,
It's SL2Z.
yeah. Why is it discretized? And I mean,
It's discretized because of the quantization, because these are states which are quantized. It's not SL2C.
So suppose you have an action,
There.
So suppose you have an action purely in terms of fermionic fields, and suppose you do a Hubbard-Stratonovich
So you have an
transform.
action of what? Say it again.
Yeah, so suppose you have an action purely in terms of fermionic fields,
Yes.
and then you do an Hubbard-Stratonovich transformation to introduce bosonic fields, and then you integrate out the fermionic problems
Yeah.
for fermionic fields. So in a sense, you've mapped a problem in fermionic fields to a problem in bosonic fields. So would you count this as a duality, or would you?
No.
Okay.
Yeah, I've done that too. Okay. And the answer is no. You only get an identification of operators in extreme regime, in what I would call in the infrared. It's not a full, you don't identify all of the operators, you only identify the currents, and only in the long distance limit. So it's essentially an effective field theory. I called it a duality in some of my papers, but it's not quite the same. It doesn't have the same footing in the sense that there are no operator identities either with that. It's only a partial identification.
Yeah, just yeah. So probably it's a too naive question. So the question is about non-locality and duality.
Yes.
So at least in the simplest case of bosonization,
Yes.
I start with a finite fermion Hilbert space, and there's a mapping of the
Not finite. What do you mean finite?
or finite fermion density, field fermion C, and then I have a mapping between the quasi-particle excitations around the Fermi surface and to bosonic picture, right? Now, if I want to add one more fermion, there's a very non-local mapping between those things.
Correct.
What is the comment about the
By the way,
non-locality?
This was true in one dimensional. So I showed you that
Yes.
if I change the sector, instead of working in the neutral sector, then I have to change the winding number.
Exactly.
Or I have to twist the fields.
Yeah. So what is the statement about non-local nature of the relation between the degrees of freedom between those parts of duality?
The usual bosonization is done in the neutral sector, where you can actually make the identification. Otherwise, you have to do it in different sectors.
Yeah. So my question is going more general.
Yeah.
It seems that the dualities, is it true that the dualities kind of are probing very non-local features of the same system between the two sides?
Yes, but they map local observables to local observables in the other theory.
I see.
Okay, so there is an aspect that I didn't cover, which is when you make these duality transformations, you have to be careful with the global boundary conditions that you have in the theory. And for instance, in the case of the mapping of the disorder phase of the Ising mode to the deconfined phase of the Z2 gauge theory, that aspect is essential because the gauge theory has a fourfold degeneration torus, whereas the Ising mode doesn't. Okay, and this has to do with these global degrees of freedom that normally one doesn't include in the duality transformation. So one has to be very careful with that. So there are global questions associated with duality as well.
Okay, so I think we have kept Eduardo long enough. And so what I suggest is if you have more questions, he's around for the next...
Until Wednesday at 6 in the morning.
Wednesday at 6 in the morning. So grab him. If you see him, just grab him. If he's sitting down to dinner, pull up a chair next to him and start bugging him. I know from personal experience that he loves to talk.
Yes.
So you will have no trouble getting him to answer you. And with that, let us thank Eduardo for a wonderful talk.